Hi everybody, today we're going to work through the free response for our practice here. We have in 2004 a spacecraft was launched and it needs to intercept a comet. So we're going to assume that the spacecraft's distance from Earth is this function here, and t is measured in years since 2004, and the y variable f of t is measured in millions of kilometers. So the first thing we do is set up our variable box. We said that t was our x variable, and t is measured in years since 2004. And then f of t, which is our y variable here, is measured in millions of kilometers. Okay, so we've got our variable box over here, and it's asking us how far is the spacecraft from Earth when t equals 2.46 years. So we're talking about this x variable over here. So what we're going to do is we're going to graph this function, and then we're going to evaluate it when x equals 2.46. Okay, so I went to the home screen, and then I went to option 1, which is new document, and I added in a graph. When you do that, you can type in your function and it graphs it for you. At that point, I had to zoom out of my Windows settings, so I went to menu, and then option 4, which is the Windows settings for zooming, and then letter A, which is zoom fit. When I was all done, my graph came out looking about like that. All you're going to need to do now is go to document, and then you're going to insert, and you want to insert a calculator because we want to evaluate this function. So we're going to evaluate the function f of 1, so you type in f1, and we're going to evaluate it at 2.46. So f1, open up a parenthesis, 2.46. And that gives us 781.247. So we write that down. The function at 2.46 years equals 781.247. Now all we need to do is use our variable here and write our sentence. So at 2.46, and then write this box right here, years since 2004. The spacecraft is, and then we already know that distance, 781.247, 781.247, and then this variable right here, millions of kilometers. From Earth. Good deal. According to this model, when would the spacecraft touch down on Earth again? So if you look back at the graph, it's a nice parabola like this, and what they're looking for is this point right here when the spacecraft touches back down. We call this a 0. This can also be a root. We also know them as solutions. They're going to, kind of give you whatever kind of terminology, nomenclature that they want. So we're just looking for that. So go back over here on your calculator, and you're going to go right up to the graph that you just made. And we're looking for this point right here, this 0. So I go to menu, and then I analyze the graph, and there it is. Option 1 is a 0. So I'm going to click to the left of where the spacecraft touches down, and then to the right again, and we get 14.222 years. So 14.222. That's this x side, right? And we know what the y value equals. At the axis, the y value is 0. So when x is 14.222, then y is 0. and that's that coordinate point. So we're going to write our sentence over here. The spacecraft lands 14.222 years since 2004. And years since 2004 is just from our x variable over here. Part C asks us at what time will Rosetta be the farthest from Earth, and determine that farthest distance that Rosetta gets from the Earth. So the farthest from Earth we're talking about here, the y variable is in millions of kilometers from Earth. So the time, or the point at which this graph shows that Rosetta is going to be the furthest away from Earth is actually this place right here, right? It's the furthest distance from Earth. It has the greatest y value, the most kilometers from Earth. So we're going to call this point, this is called a maximum, and we're going to find that point on our calculator. So let's take a look. We're going to come over here, and we're going to find the maximum. We're going to go to Menu, and then we need to analyze the graph, option 6. So you're going to hit maximum, which is option 3, and then we'll come over here to the very tallest point of our graph. Okay. So you see there, it's 7.111 years, and let's find that other point here. 7.111 years, and then the y value is 1.365.333. So 1,365.333. Alright, and that's our coordinate point of the maximum. So all we need to do is write this along with all of our variables, and we'll have our sentence here. So the x value, again, is measured in t years since 2004. So at 7.111 years since 2004, Rosetta is 1,365.333 millions of kilometers from Earth. Great. We've got one more question down here. It says, at what time is the y greater than 756? So use correct units, interpret the meaning of the context of the problem. So we need a y line, y, greater than 756. So let's go ahead and have the calculator do that for us. We are going to go to Menu, and we're going to add in a line. We want the line to be 756. When we do that, it's going to show our lines coming across here, right? And so you see that your spacecraft touches the line here, and then also here on the other side. So we're going to find both of those points of intersection, and that'll finish this up here. So let's take a look. We're going to go to Menu, Analyze the Graph, and then option 4, we're trying to find the intersection. We will find those 2 points. So the intersection happens here, and we're going to write down that coordinate point, and then it also happens on the other side. So we've got 2.3605 is our first one, and then our second one will happen when we go to Menu, Analyze Graph, find the intersection. This also happens on the far side. Also over here at at positive 11.8617. So now we know that our function crosses the line at these 2 times, and that's what it's asking. What times does this happen? So we just need to interpret this. This is years since 2004. So that's what we're going to put in there, years since 2004. Alright. At 2.361 and 11.862 years since 2004, the spacecraft is 756, and that again, 756 was measured in millions of kilometers. So 756 million kilometers from Earth. They give us a follow-up question on the back. So let's take a look. It wants us to determine the average rate of change on the interval 8.1 to 9.7 with appropriate units. So is it telling us that the spacecraft is getting closer or farther away from Earth over that interval? So essentially, you've got your parabola here, and we're going to measure the 2 times that this happens, and then we're going to take the slope. And if the slope is negative, then we know that the spacecraft's coming back to Earth. If the slope is positive, we know that the spacecraft is just leaving Earth. So we're going to test those 2 points. So the first thing we're going to do is find out exactly what these coordinate points are. So they're giving me the x values of the coordinate points, and I need the y value. So 8.1 comma something, and then 9.7 comma something. And we were trying to get these coordinate points so we can take the slope. So we've got our function in here, just like that, and we're going to evaluate it for 8.1 and 9.7. So we'll come over here, and we can insert a new calculator, or we can just go back to this other tab where we already had done some calculations. And we can type in F1, open up a parenthesis, and then put in 8.1. That gives us 1,338.930. So 1,338.930. And then we'll evaluate F1 at 9.7. That gives us 1,184.370. 1,184.370. So those are our 2 coordinate points. And you can already kind of tell on the y side, it's going down, but on the x side, as time goes on, we're sort of increasing in time. So let's take a look at the slope. Delta y minus delta x, delta y over delta x, excuse me. So we're going to do y2 minus y1 over x2 minus x1. That's 1184.370 minus this y value, 1,338.930. So let's set it up, and then we will finish this problem up. 1184.370 minus 1,338.930 divided by, and this is 9.7 minus 8.1. So now you can match it up. This part of the coordinate point's right here. This part of the coordinate point is right here. They need to be right over each other. Okay, so when you set it up, you solve it out, and the next step that you're going to do is divide, and that comes out to negative 96.6. So now that we know that our rate of change is negative, we know that the slope over here is negative, so we're on the back side of this. So in other words, what's happening is Rosetta is getting closer to Earth because the slope is negative. Rosetta is getting closer to Earth because the slope is negative. If the slope had been positive, again, we would have been on this side of the parabola with a positive slope, and we would have known that Rosetta was getting further away from Earth, not closer. So that's the other way.